So now we begin the last chapter of Math 5A. Chapter 5 is applications of integration, and section 5.1 is the area between curves. So now we'll be finding if we have one function, if we have another function, how can we find the area in between them? And we can find that using integration. So we have a lot of chapter 5, which is basically just a lot. There's a lot of pages that are just definitions and explanations, and then we get to the actual doing. So notice that you want an area that's bounded by two curves, and that has either the two curves intersect, or maybe you just have from here to here, and you're trying to find the area in between. As long as the function, one function is greater than the other function for the whole time on the interval, then the area bounded by them is found from the formula that you see here on the screen. So this is still the idea of a bunch of rectangles. It's just that when you look at this piece, this is the height of the rectangle, and that height is simply the difference in the y values, because that's how tall each rectangle is. And then of course you still have your change in x, which is the base of the rectangle. So now it's really just, as opposed to the height of the rectangle being the difference between the function, the y value, and the x-axis, now it's the difference between the two functions, the two y values. That's the height. So that's really the only difference here. But that does create an integral, because once you take the limit of that, and you shouldn't be surprised to see that it's simply subtracting the two functions together, and with your differential there, dx, and your limits of integration from a to b, which is the interval that it's on. So the next picture shows it better. So we have our picture here. You can kind of see what's happening. You don't have to worry. We will not be doing these by hand. We will just do them using integration. But it's just a bunch of rectangles that are created, and the height of that rectangle is this y value, subtract this y value, so that's the height of it, and then you've got your like width of it, basically, and that's your delta x. And if you take, you know, more and more of these rectangles and you make that change in x, that delta x, smaller and smaller, and just shove in a bunch of rectangles, you're going to get a very good approximation. If you take that limit, you're going to get the exact area between the curves. So what's happening for the rest of the page is really just the idea of actually taking these rectangles and what would happen. So we won't spend too much time on this, but you want to understand that the area of the first rectangle, and we're looking at all of the values here as just some sampling point, because remember, that could be anything. It doesn't have to be left hand, right hand, or midpoint. But each rectangle, the area of that rectangle is just going to be the difference in the one function minus the difference, the y value, you know, from the other function. Call that g. It's not very exciting. And then multiplied by the delta x. And then you have your next interval, and that's going to give you a sub 2. I think you guys see where I'm going with this. So again, times the delta x, so it's just the height times the width for any rectangle. And then we'd have another one. Don't worry, I won't do this every section. And that would be your third rectangle. And again, you could do this infinitely many times. So the area between the curves can be estimated using this idea of the limit, which is just taking every single possible sampling value, putting that into f and g and subtracting, and then multiplying by the delta x. And then once you think of that in terms of going from, you know, as n goes to infinity and a ton of rectangles, then you're going to get integration. So this is the exact area. This is the key thing and what's important for our purposes, but understand that it simply comes from adding up an infinite number of rectangles under a curve, well, between two curves in this case. So let's take a look at an example. So find the area bounded by the curves f of x equals x squared minus 4x plus 10, and g of x, 4x is minus x squared, from 1 to 3. So what I would probably do to start this is I would kind of show what my area is. So from 1 to 3, I would do this. And this is the amount of area that I'm trying to find. All of my scaling here is by 1, so you can see that you could kind of even get an estimate of what you think your answer should be by understanding how many of those little 1 unit squareds you have that are being shaded. So, you know, just thinking about this, if this is 2 and we're kind of going from here to here, and that's a difference of 4 from 3 to 7, you should think that the area, and this is not required, I'm just telling you that, you should think about the area as being, you know, greater than, say, 4 and less than 8. So the reason I say that is because you can see that it's greater than 4 because we've already shaded 4 little unit squareds, but we know that it's less than 8 because 8 would consider everything, including this space up here and this space down here, which we know we don't have. So just as an idea, like our answer should be between 4 and 8 to think about it. So following the definition, we're going to integrate from 1 to 3. And then the important thing is to think about which function is on top. And this sometimes is given to you in the picture, and sometimes you have to figure out which function is on top. But we know that we have 2 parabolas, and that one of them is up like a cup, and one of them is down like a frown. And if you look at the 2, you've probably recognized that the fact that the first one, the f of x, is x squared, tells us that that should be up like a cup. With the other one, we have a negative x squared. So it's going to be down like a frown. So we want to take our function that's always on top, because again, this is the height of our rectangle at any point in time, is the f of x minus the g of x. So we should have this. And I'm going to put this in extra parentheses here and then do a dx. So every single value there in my big brackets is the height, because it's one y value minus another y value. Then I think the easiest thing is to simplify this. So you're going to have x squared. It's going to be a plus x squared to get a 2x squared, because minus minus. You're going to have a minus 4x and then another minus 4x, so minus 8x. And then you have a plus 10, and nothing happens with that. So you can pull that out and have dx. Now, if you want to tell me if it's possible to pull out the 2, you could pull out the 2 if you wanted to. That would be no problem if you don't want to deal with such a big constant. Not that that's huge, but it would simplify what you have a little bit. If you're into that, that is your choice. Notice that this does not use any crazy integration methods. It is simply a quadratic that we just need to integrate. So I'm going to pull the 2 out, and then I'm going to write 1/3 x cubed. I'll have a minus 2x squared plus 5. Remember, you can always pause this, see if you can get the answer. And that's going to go from 1 to 3. And then all we have to do now is just evaluate. So now we're using the fundamental theorem of calculus part 2 here. We have our antiderivative, and we are filling in our a and our b. So when I put in 3, I'll get 3 cubed divided by 3, which is 9. And then I will get 9 times 2, which is 18. And then I'll add 15. Then I'm going to subtract what happens when we put in 1, which is 1/3 minus 2 plus 5. And again, we're just seeing what numbers we have. And if we do that, everything should hopefully work out, and we should get 5 1/3. And I'm going to say units squared because it does ask me to find the area. So that tells me, hey, I should probably use a unit squared, which you should. But that's all that it is. That's all that section 5.1 is. I mean, that's not it. Let me do another one to show you a slight difference in what you have. Possibly. You know, what is possible. Whew. All right, find the area bounded by the curves. So the big thing here to notice is that you have two polynomials, but they intersect at multiple locations. And the key thing to see here is if you were to guess which function is this one. So notice that this one does this. And so you probably guess that this is negative x squared plus 3x. Then this function over here is your cubed. And of course, you may notice that because they intersect, they actually change which function is on top and which is on bottom. So because of that, it does require two integrals. Because if not, you are going to get a negative area instead of the positive area. These should always be positive because you're finding the area between curves. So the answer should always be positive. So two integrals, that's what's needed here. So we'll do our first integral, limits of integration. Anybody want to take a guess? So I'm going to start from the left and go to the right. When I go from -2 to 0, I'm going to take the function that's on top. I'm going to subtract the function that is on bottom. And that will be my first integral. So I put this, I don't forget my dx to say that I'm integrating with respect to x. And then we also need to come up with our second integral. So that is going to be plus, and then we have from 0 to 2. There's no symmetry here, so don't think that you can do something to make your life easier. But from 0 to 2, what we notice is, in this case, that parabola is on the top. So that's our upper function. And then we need to subtract our lower function. So that is the 2x cubed minus x squared minus 5x and dx. So now we have our two integrals, and now all we need to do is integrate. So I will first simplify just to make my my integrals look better, kind of easier to deal with, and hopefully I'm okay with spacing. So I'm going to go from 0 to 2. It looks like we'll have 2x cubed. I have a negative x squared, and then I have a minus a negative x squared, so that's plus x squared, so that's gone. And then I have a negative 5x minus 3x, so it looks like I'll have a negative 8x. And that's it. Okay. Then I have, don't forget, I gotta write my correct notation. Then we'll have from 0 to 2. So in this case, I have a negative 2x cubed. Then I have a negative x squared minus a negative x squared. Well, that's gone. Then we'll have a 3x minus a negative 5x. So notice the difference between the two integrals. Very, very similar. Very similar. Opposite only by that a negative, and then of course different limits of integration, which are going to give you different values here. But at this point, now all we have to do is just integrate and evaluate, and we'll be done. So now we have add 1, so 1 half x to the 4th minus 4x squared, integrating from -2 to 0. And then we have a negative 1 half x to the 4th plus 4x squared, and that is from 0 to 2. So when we put in 0, we will just get 0. This is into our first limits of integration here. So we get 0, then we're going to subtract what happens when we put in -2. -2 to the 4th is 16, times a half is 8, minus, when we plug in -2, we get -2 squared, which is 4, times 4 is 16, so minus 16. And then here, now we're going to add what happens when we put in 2. So 2 to the 4th is 16 times negative 1/2 is negative 8. And then plus what happens when we put in 2, and we're going to get 16 there. So notice again that pattern. And then we just subtract what happens when we put in 0, but we get 0. So notice we're going to get an 8 plus, and then over here another 8. So that gives us 16 units squared. So in this case, understand that we're doing A to B. So if I call, say, this y1 and this y2, in this case we did from A to B y1 minus y2 dx, and then plus, basically going from B to C, y2 minus y1. So that's not uncommon. If you have two functions that intersect at a value, then you may end up with more than one integral. And we'll look at an example, but if somebody says, well, what if I don't have the picture, which could probably end up in the discussion, we would set the two functions equal to each other to see what x values they share, because the x values they share is where they share intersection points. They have intersection points, and that will tell us what values we need to think about in terms of integrating to and from.